Okay, pre-calcers. So today we're going to be looking at finding intersections of conic sections. And just like intersections of polar graphs, we're really just solving systems. And so we're going to start off by solving our system algebraically. So you can use all of the same tools and resources that you have for solving using the elimination or the substitution method that we've done in the past. And then when we're done, we're going to show that the points are actually intersections by drawing a graph. So we're going to use part of our graph paper for the graph and then the other part for solving. So I'm looking at this particular system, and since I have an x squared and I have an x squared here, I'm leaning towards using the substitution method. Sometimes you'll be able to solve using the substitution method, sometimes you'll be able to solve using the elimination method. There are some times where the elimination method does not work. In this particular case, the elimination method absolutely works. What you have to be careful of is we can't try to eliminate our y's because we have a y squared and a y. And so we would still have an extra variable in there. So after your first step in the elimination, if you find that you didn't actually eliminate anything and you still have two variables, then just go back and try another method. So in this case, I'm looking at x squared and negative x squared. If I add these two equations together, I will have eliminated my x squareds. So I'm going to go ahead and do that. So I'm going to add them together. So then I'm going to end up with y squared plus y on this side equals 20. Okay, so then I can write it as y squared plus y minus 20 equals 0, and then factor. Once we've factored, then we can say, okay, y is either positive 4 or negative 5. So that's one part of our solution, but remember we also need our x value, so then go ahead and plug it into either equation, whichever is going to be easiest. So I'm going to use the first one because it doesn't matter, and the reason I want to choose the first one is because it has x squared instead of negative x squared, and so it'll save me with that one extra step. So I'm going to say x squared plus 4 squared equals 25, or x squared plus negative 5 squared equals 25. Okay, so we're plugging each one in, and then we can solve each of these for x. For both of these, we're going to end up square rooting to solve, so don't forget when you do that step the plus and minus. So we end up with plus and minus 3 from substituting in 4, and 0 when we substituted in negative 5. But be careful, because we can't mix and match these. Our solutions, the 4 only goes with the plus and minus 3, and the negative 5 only goes with the 0. So our solutions are 3, 4, negative 3, 4, and 0, negative 5. There are no additional solutions. So that's the first half of our intersections problems. So we have to find the intersection points. Then the second half is showing that there are intersection points by drawing and clearly labeling our graph. And so then for this, I'm looking first at my first equation, and I can recognize that it's a circle. And when I go to draw that circle, I can divide everything by 25 to rewrite it in graphing form. If that helps, go ahead and do it. So I can tell it's a circle centered at the origin with a radius of 5. Okay, then I'm looking at my second equation, and it's not a circle. There's only one squared variable. This is a parabola. So I'm going to put it into graphing form. And remember, graphing form is just vertex form. So I'm going to move my x squared to the other side. I'm going to move my constant over to the y. So it's going to be y plus 5 equals x squared. So it's a parabola. Because x is squared, it opens up, down. Or the coefficient is positive, so it opens up. It's standard width. And the vertex is at 0, negative 5. So knowing all of this, I know I need to see the origin for this and see 5 in all directions. And then here we just need to make sure we're going out to 5. So if we put our axis in the middle here, that's fine. So go ahead and set up your axis. So once you have your axis set up, then we can plot our circle centered at the origin, and you're not labeling a whole bunch, you're just drawing the picture. And just like with our intersections on our polar graphs, it's going to be really beneficial to us if we draw in our intersection points, because they have to lie on both curves. And it's really easy to draw a sloppy circle, and so it's going to be nicer if we have these points labeled already. So 0, -5, we can call that one C. 3, 4. -3, 4. So those are intersection points that have to lie on both curves. But what I'm noticing is, because I have this perfect circle here, there's a lot of symmetry. And so this A point can be reflected. It's right 3 up 4. It can be reflected down here. Similarly, the B point can be reflected. Now that doesn't mean that those points lie on both curves, but it does mean that those lie on the circle. And even more than that, I can tell that 3 away and 1 down from any point that's on one of these axes will be on the circle. So I can even include these points that are 3 away from the others and 1 away. So we can draw the best circle possible with all of that information. Okay, so now that we have our circle, we can go ahead and draw in our parabola. So it opens up vertex at 0, -5, that's our point C, and we also have these other 2 points, but then we remember for parabolas, since it's standard width, we're going to go right and left 1 up 1, over 2 up 4, over 3 up 9, and you can verify that those are the correct points, and then over 4 up 16. And I'll just keep those as points in mind, so I can draw the best parabola I can. Okay, and if you hadn't yet labeled your intersection points, make sure to do so now. You can label them with ordered pairs or letters. Okay, so we solve algebraically and then demonstrate that those points are in fact intersection points by graphing them. Okay, so our next system of conic sections, the second one is actually something slightly different. This one we can see we can't use the substitution method, the elimination method to solve this one. We're going to have to use substitution. And since we also will have to graph this, I figure we might as well solve this second equation for y while we're at it. Okay, so we can write this as y equals 8 over x by dividing both sides by x. And we actually saw this at the very beginning of the year. We saw different equations like this where we started out with just a 1 on top, and then we did our whole unit on rational functions. And the picture of this graph, we're going to have to keep this in mind, looks like this. Okay, so we'll kind of keep that in the back of our mind, and then we'll use specific points to plot it. All right, so now that we have that, we can substitute our expression into the other equation, just using the substitution method. And then go ahead and solve this algebraically. At this point, I'm going to multiply everything by x squared so that I don't have that denominator anymore, and then just distribute it through. And then we can set this up for factoring. And remember, if you have an even power, like x to the 4th and then x squared as your middle term, that factors in much the same way that it would have if you had a square and then a linear term here. So go ahead and set up your factoring. And the one difference is that you're going to have x squared in both of these instead of x and x. Okay, so go ahead and factor that. Okay, so once we have our first factors, then hopefully you notice that each of these are a difference of squares, since they're both subtraction and 4 and 64 are perfect squares. So we can actually keep going. So we have x plus 2, x minus 2 from x squared minus 4, and x plus 8, x minus 8 from x squared minus 64. Now it's completely factored, and we can see we have x equals negative 2, positive 2, negative 8, and positive 8. Each one of those we're going to need a y value. So that's where we're going to go to our y version of the second equation. You can of course plug it in here, but since it's already solved for y, that's going to be easier. So I'm going to say for x is negative 2, y is 8 divided by negative 2. So each one, and you can of course do that step mentally, and then we end up with negative 4, 4, negative 1, and 1. Okay, so our ordered pairs, and I think I've run out of room here. So our ordered pairs for this one, remember that they have to match up. We can't pick and choose, mix and match. Okay, so we have negative 2 goes with negative 4 only. Positive 2 only goes with positive 4, and so on. You can go ahead and name them. So then we have the general shape of our second equation, and we can see it's centered around the origin, so we will need to go out, and even from your points, out to 8 in both directions, so we have to keep that in mind. Then if we look at our first equation, that's actually an ellipse. Okay, we can divide everything by 68, and it's okay to have decimals here. Oops. Okay, and so we end up with x squared over 68 plus y squared over 17 equals 1. So when we include those denominators into the parentheses, you're going to have decimals, which on these decimals are okay because we're just using them to see the graph, where if you were doing this on one of the analysis problems, we would leave root 68, or actually would simplify it and root 17 in here. But instead I'm just going to find those. And don't worry too much about the rounding because we're just using it for graphing purposes. One space is perfectly fine for that. Okay, so we have 8.2 and 4.1. So we know it's centered at the origin. Okay, and going out a little bit more than 8 in the x direction, and a little bit more than 4 in the y direction. So if we set our axes right in the middle, we can go out to 8, hopefully, in almost all the directions. So go ahead and set up your axes. Okay, so I'm going to start with my intersection points. Oops, not that one. Negative 2, negative 4, positive 2, positive 4. Okay, and we can then name these as well. Okay, so let's start with the strange one. It's actually a hyperbola that's been rotated, but don't worry about it being a hyperbola. We can just graph it like we did in the fall. So what I'm going to do for this is I'm going to plug in numbers that are going to be nice in here. So for example, when x is 1, y is going to be 8 divided by 1. And plot that. Now I know b is in there. That's when x is 2. 8 divided by 2 is 4, so it makes sense. And I have this point. So what about another nice number like 4? 8 divided by 4 is 2. So when x is 4, y is going to be 2. And so now I can see the sequence of points. And remember that your x and y axes are both asymptotes, because we can't divide by 0. If we had solved this for x, we can't divide by 0 there either. And we can do the same thing over here. We're going to have when x is -1, y will be -8. When x is -2, y is -4. And when x is -4, y is -2. And then we also have our point C, and that works out as well. So approaching those asymptotes of the x and y axes. All right, so now we just need to draw in our ellipse centered at the origin, going out 8 and a little bit in the x direction, and going up and down 4 and a little bit in the y direction. And then we have these points B and D and A and C. I'm going to use symmetry again. I'm going to reflect B over here. And I'm going to reflect B downward, or you can think of reflecting A horizontally. I'm going to reflect D downward and C upward. So now we have a lot more points to go on. So we can then draw our ellipse through there. So go ahead and draw your ellipse, and then you have your intersection problem done. Okay, so it sort of looks like a spaceship, like where the Jetsons live. All right, so now you know how to find intersections of conic sections.